Mhm.
Perfect. All right. Welcome back, everybody. Thanks for coming to our second workshop. Today, we're going to be talking mostly about feeding forward and back propagation, going more in depth on neural networks than we did last workshop. So let's go next slide. Again, it's going to be me. We have Justin here, and Paymon and Vaishnavi is also here. We'll be teaching these workshops. Today, it's going to be mainly me and Paymon speaking. Here's our tentative schedule of our workshop series. Last week was logistic regression review, and then a little bit of an intro for our neural networks. This week we're going to be mainly focusing on backpropagation and feed forward, the parts of the neural networks, and then next week we'll be going over convolutional neural networks. So as a review exercise to get us started and to review what we did last week, what does it mean to say that a neural network is learning, at least with respect to linear and logistic regression? If you have an answer, you can say it, or you can either unmute yourself or you can say something in chat.
Yeah, we encourage you guys to unmute yourself. So think about the ways that we discussed, like, wait, the code is great. Okay.
Oh, okay.
Yeah,
I
anyway,
might have pasted the wrong code in. It's my fault. I'm sorry
that's
about
all
that.
good. So think about the ways we discussed that you can evaluate these model architectures, right? So we talked about how we have to have a criteria to evaluate the model, right? And we use that criteria to determine how the model's doing. So please, like, if you guys remember some things that we discussed last week, feel free to unmute yourself and give your hand at some of these questions. We want to, I know it's hard at first to be the first person to unmute, but I promise everyone will thank you, and it'll make it a more interactive and productive environment, I think. Even if yeah, go ahead.
You go ahead. Oh, sorry. Yeah. I was just gonna say, like, if the loss function approaches 0 or like during the training phase of the data set.
Yeah, so that's a good answer, right? So the loss function is some function that we use to evaluate the performance of our model, right? And we discussed last week briefly ways in which all the model knows that it's doing is that it wants to reduce the cost function. So in the eyes of the model, its job is to reduce the value that the cost function outputs. That's all it knows that it's doing. It just so happens that we define the cost function in a way so that if the cost function has a low value, then that must mean, by definition of how we define the cost function, that it's basically doing a good job of classifying things. So that's a good way to see if something's learning. Now, we also discussed last week briefly, we're going to go into this in more depth, but we briefly discussed overfitting and what that means and sort of why that's bad. We didn't really talk about ways to avoid it too much, but can someone try to recall what overfitting is and kind of possibly, like, we discussed briefly last time, ways that things that cause overfitting, little things we can do to help reduce it. And we're going to discuss this more, but we discussed it briefly last time. So if anyone remembers, feel free to unmute or chat.
Overfitting was fitting the data set too well, but generalizing poorly.
Yeah, exactly. That's a very succinct and good way of describing it. So the way what I told you guys last week was kind of when you guys are students, right, in a class, you're given homework assignments, right? And a lot of times maybe you're really overwhelmed, so you just kind of memorize how to do that homework problem, and you maybe get the correct answer, or maybe you didn't actually understand the concepts behind that homework problem, you just got the answer. And then when you go to take the exam, you do a really poor job because you didn't actually understand the concepts, you didn't actually understand how to generalize them. So that's the same exact thing in neural networks. So what we do generally is that we train the network on this training set, right? And we're going to talk about the different sets that we use today a lot more. But we use a training set to train the network at first, hence the name, right? And then after we've trained the model, we evaluate the model's accuracy on a test set, which, as the name implies, is like kind of like the exam that a student would be given, right? So it's important that the model can not only do a good job classifying on the training set, but also on the test set, because the test set is composed of things that the model has never seen before, right? So if our model's doing a good job on the test set, that means it's generalizing well, which means it's not overfitting, and we don't want overfitting generally. So yeah, good answer. I think we can move on. So
Yeah.
Ben's gonna walk you guys through we're gonna do a quick review of the first few slides of what we talked about last week, just to make sure we're getting a better understanding. Then we're gonna dive into neural networks. So go ahead, Ben.
Another thing I want to add about that is just that the point of this question, or the point of talking about overfitting, is that we want to always keep in mind that the overall goal is to build a network that can generalize the data it hasn't seen before. Even though the whole training process is focused on minimizing that cost function, that's not our overall goal with when we're doing this training process. Right. So, actually, before we get into it, there's actually a couple of things I forgot to mention before we start. There's a couple other events that are going on with ACM. One of them is Demystifying AI. That's happening tomorrow. It's a one-off event, and it's focused on talking. It's the main audience is for people who aren't really familiar with AIs. So, not exactly you guys, but it will go over a lot of topics that are more moral or ethical in nature, right? It will also talk about things like having a data set that might be biased towards biased in certain ways, and the consequences of that, both technically and like socially. So there's a lot of good content there, and I highly encourage you guys to check it out if you have the chance. Another thing is our intern applications are out. So I think we're only taking one position. Correct me if I'm wrong, but there are also positions open for other committees in ACM, and you can apply to multiple positions. I think someone asked that last workshop as well. But applications are open now. If you are interested and you want to join one of our committees, this is sort of the pipeline that people take to become like one of us who's teaching these workshops, or working on other things like the projects team that we have in ACM AI.
Yeah, so Vaishnavi gave you guys links just now to the first one is for Demystifying AI. The second one is for the internship app. I believe both of those. I know for sure the internship app should be in the newsletter if you guys are on the ACM wide newsletter. So that's there. So just to recap, you guys can apply to more than one position. And when we say that, we're talking about different subcommittees. So for example, you can apply to a position with us, and then you can also apply to a position with like ACM Hack, and then another one with like ICPC. So you can apply to multiple, and you can get interviewed or whatever for multiple of them. But I think ultimately, you're only allowed to accept one of the offers. But just keep that in mind.
And also another thing is our Discord. I know some of you watched this afterwards, and you can't like ask us questions like in chat. So you can ask us questions. You can ask them in Discord instead, and we'll try to answer them as fast as possible. We're all watching the Discord channel. We got a couple questions last week, and I think they're really great questions, and that's actually. It helps us inform us of like things that we might have missed, and also we'll try to go over it the following week as well if it's especially important. But yeah, since we know that a lot of you guys are on different time zones and you can't make it to these workshops in person, please use the Discord channel if you have any questions or you want to interact with us. And there's other channels for other topics as well if you're interested. All right, so I think we can start with our first topic, which is revisiting the math behind gradient descent. This is going to be a lot of the same slides from the last workshop, but I'll probably go over some things that we missed and other things in more detail. So first off is our hypothesis function. Again, this is basically the constraint, right? Remember, with machine learning, we're taking inputs and outputs, and we're trying to compute a mapping between those two. Our hypothesis function is putting a restriction on that. We're saying that we're only optimizing this set of functions, and this set of functions being linear functions for linear and logistic regression. For a single feature, we have a single weight and a single x value. So this is a single scalar for both w and x. And we might also have a bias. For multiple features, it's the same idea, except we add them on. So you might have weight 1, weight 2, and weight all the way to weight n. So each of these x1, x2 to xn are scalars, and those represent individual features. So these individual features can be like different values, different pixel values in a picture, or it can be things like the housing price or the amount of rainfall on a particular day. And you can have, and you can combine multiple of them to allow the network to draw upon this information to make their predictions.
Yeah, and I want to pose a question to you guys again about this. So we discussed learnable parameters last week. So when you're looking at this hypothesis function, you see a bias term, you see some weight terms, and you see some input terms. So of the B, the W's, and the X's, can someone unmute and tell me which ones of these are considered learnable parameters, and why these are considered learnable parameters? You can also use the chat if you really don't want to unmute.
The weights are the learnable parameters, and the bias is just like the default based on which function you choose.
That's great. Actually, sometimes we'd also consider the bias to be a learnable parameter as well. You can also change the bias. We'll actually talk a bit in more detail. There's actually a little short video that talks specifically about the role of the bias, but it can also be changed as well, similar to the weights.
Yeah, so we consider learnable parameters to be parameters that basically the network has the freedom to play around with when it's learning. And this is in contrast to what we also discussed last week, which are hyperparameters. Hyperparameters are parameters that we choose for the model, and it is going to have certain implications for the way the model functions and its performance. So a lot of the parameters are things we let the model learn itself, which is what the heart of machine learning really is. And then a lot of the parameters we kind of have to choose ourselves. So yeah, just remember the weights and the biases we consider learnable parameters.
Yeah, well, thanks for asking that, or thanks for answering that. We really appreciate the participation. Right, so I wanted to give a little bit of an example. I think it was on the last week's slides as well, but I wanted to ask a little question about this. So this is an example of, oh, there's some missing, there we go. So the line here, the red line here shows the predicted value. So this is sort of like the hypothesis function. And the green dots are the actual data that we're training on, right? The y-axis here is the output, and then the x-axis is sort of the input, right? My question is, how many features do you think this model has? You can either answer in the chat or if you want to unmute.
Someone besides Samuel this time.
So just say like, or I'll make the, I'll restrict the answer. So either 1, 2, or 3. 1. Okay, I'm seeing ones.
Okay.
Perfect. Okay, great. Yeah, so there is only one, and the reason for that is, well, there's only one x-axis. So there can only be one feature that we have in this model. So if you imagine, if you had a model that took in multiple features, let's say 2 features, then this would be a 3D graph, right? So you'd have 2 axes like the x and y axis, and those would be 2 features, and then the y-axis would be the prediction. Now, how would you represent this? How would you represent multiple outputs? Does anyone have any idea? This is more open-ended, so you can't just like throw out a number.
Ben, do you want to clarify what you mean by multiple outputs?
Right. By multiple outputs, I mean like multiple scalar outputs. So in this case, the y-axis, the y value is an output, right? So if you had multiple outputs, how would that be represented? Or how would that actually even, how would that work, kind of. You can give any answer. There's no like wrong answers here. I actually, well, yeah. Okay, I'll make it. I'll give you a couple options then. Will we add another axis like we did within the feature, or maybe we can add another plot entirely? Would it be a new plot or a new axis?
We'd be a new plot. No.
Yes, right. That's exactly right. We would need an entirely new plot. So it's kind of like just having a separate model, a second model, since the output is only, it can only be one value here, one scalar value. Right. So now that we have the hypothesis function, we need a way of determining how close our predictions are to the ground truth. And that's the role of the cost function. In this case, there's more than one possible cost function. The cost function we're showing here is mean squared error. And I think I mentioned before, but it's mean squared error because we're taking the error, which is y minus y hat. We're taking the square of that. So it's sort of like taking the absolute value. And then we're averaging that across all the samples in our training data set. Other possible cost functions could be like taking the absolute value instead of the square, or you could also do something like taking it to the power of 4 instead. The reason we do to the power, we square it instead of doing like an absolute value or doing it to the power of 4 is because taking the derivative of this function is actually pretty easy or pretty nice to do. And we'll go over that in this workshop in more detail. Ignore that line about an aesthetic 1/2 factor. So when you take the derivative of this function, the exponent 2 comes down to become the coefficient, right? So sometimes you actually have a 1/2 constant multiplied to kind of cancel that out. But that it doesn't really matter when you're optimizing, right? Because it's a constant value. So now that we have a hypothesis function and then a cost function to measure how well it's doing, we need an algorithm that adjusts the weights of the hypothesis function in order to reduce the cost, or to reduce the overall cost. So our goal is to minimize the loss. The loss is another term for the cost function as well. And we do this by taking the partial derivatives. I don't think we made a multivariable calculus a prereq for these workshops. So in the next slide, we actually have a couple problems to show you how multivariable calculus works if you haven't taken it before, because I know some of you are coming straight from high school and might not have taken these classes yet. Please don't be scared away by it. You won't have to understand a lot of multivariable calculus to understand how this works. And all you need to know is actually on the next slide right here. And I'll go to it right now. So here are a couple exercises for partial derivatives. We have a function. You can think of it like a hypothesis function h that takes in two variables, y and z, and computes y times e to the power of negative z. We want to calculate two expressions here: the partial derivative of h with respect to y and the partial derivative of h with respect to z. So for those of you who haven't taken multivariable calculus yet, what we mean by taking the derivative of h with respect to y is that we're treating all other variables except y. Actually, can you guys see my cursor on the screen right now? I just wanted to point at it.
You're good.
Okay, great. So for this, if we're calculating this expression here, right, the partial derivative of h with respect to y, what we're doing is we're treating all other variables, in this case, there's only one other variable, z, as constants. And then we take the derivative as if, it's just a normal derivative.
Yeah, so pretend like the z is like, so if you guys are like how you learned in integral calculus for like a, b, and b, c. So like pretend the z is like a constant. So pretend it's like the number 5 and then take the derivative like you normally would, right?
Mm-hmm.
And then for the z, pretend that the y is like the number 5 and then take the derivative. That's when I remember when I was first learning it, that's what made it easy for me, is in my head was literally like think of those constant values as numbers, compute it and then like realize, well, like understand that they're not numbers, right? But you treat them like constants. So can you guys take 2 or 3 minutes to like do this, and then just like say it in the you can just like type the answers in the chat as you get them.
Mhm.
So don't really worry about like what this means in terms of hypothesis function. Just like it's a function with 2 inputs and it yields a single output, right?
Yep.
So all you have to worry about.
Yeah. So just for this first one, we're doing the first one, the partial of h with respect to. Actually, no, you need to do both because the next transition is going to show both answers.
Is anyone like confused by how it works or what you're doing? Okay, yeah, I see some people typing answers.
Yep.
Okay, so these are correct answers. Then do you want to?
Yeah.
Do you want to show? So do you want to just explain kind of how we got those answers?
Yeah. So.
Or even the people that answered, if you want to walk us through your thought process, maybe.
Oh yeah, that's even better.
Good idea.
So if you guys want to unmute or explain in chat, that would be great.
Yeah, don't be shy.
I can just say it.
Okay, thanks.
So for the first one, when you take it with respect to with respect to the y part, you like essentially like what you guys said, e to the negative z just becomes a constant. So then once you take the derivative of y, it would essentially you just have the constant left. And then for the second one, essentially y now is the constant. So then you just take the derivative of e to the z, and then you just bring the negative down because e to the whatever is just the same. So then that's just how I got the second one.
Perfect. Thank you.
Yeah, so for the just to make sure that's clear to everyone. So like in the first one, the quantity e to the negative z is like a constant, right? So pretend, like I said, it's like the number 5. So if you differentiate 5 times y, right? The y goes away, right? And you just are left with 5. You're just left with that constant. So that's why here you're just left with that constant, right? And then for the second one, now the y is a constant. So pretend you're differentiating 5 times e to the negative z, right? Well, all you have to do is use chain rule. You pull down that times -1, right? So that's where that negative sign comes from, and then that constant y just remains untouched. So you're left with negative y times e to the negative c.
Right. So we have a last problem, which is z of s of u is equal to s squared plus s times u plus u squared. And it's just, we'd like you to do the same thing, which is take the partial derivative of z with respect to s, and then the partial derivative of z with respect to u. And we'll reveal the answers in just a moment.
Yeah, I think this one's even easier, so it's good. Okay, we're getting some answers. Okay.
Oh yeah, no, I got it.
Well, what happened?
No, I think wait.
Okay, so
No,
does someone wanna unmute again? Just let's go quickly so we can get to the juicy stuff.
I guess I could go.
Yeah, go ahead.
Yeah, so the s squared term becomes 2s for the partial derivative with respect to s, and then for the su term, the u is a constant. So then it would just be 2s plus u, and then for the partial derivative with respect to u, it's just the same thing, but because the u squared will become 2u, and then the us term, the s will be constant, so plus s.
Cool.
Awesome. Thank you.
Okay. So does everyone please like speak now or forever hold your peace or whatever? Okay, just kidding. But like, it's really important that you guys understand this like what we're doing when we're taking a partial derivative. Otherwise, you might not have too much fun later in this workshop. But I think most of you guys understand what's going on here. But please, if you don't, just like say something now and we can take a second.
I mean, if you do get confused later on, we'll do a little bit more. We'll do a few more partial derivatives later on. Yeah, feel free to ask for clarification. We'll try to go through it again.
Yeah, and we're gonna be like walking through like some of the actual partial derivative calculations for applicable examples like on the loss function and stuff, and then you'll get more practice seeing how that works there as well. So I think we can move on, Ben.
Yeah. All right. Let's go on back to gradient descent. So there was a bit of a question, I think, last week, or a bit of.
Oh, Ben, I accidentally muted you. Can you unmute? I was trying to let someone in.
I got the notification. Don't worry. So where was I? Last week, I think there was a little confusion about how the gradient descent algorithm works. We kind of glossed over the fact that it's iterative. So every time we run through the algorithm, that means like doing a feed forward, making our predictions, getting the difference of those predictions with the ground truth, and then adjusting the parameters. That's just one iteration of the algorithm. So in this diagram, it's just one of the hops from this point to this point. If we continue doing this until we reach a global minimum, and we can tell when we reach, or a local minimum, we can tell when we reach one of these minimums by the fact that every time, if we keep iterating, you can see that it doesn't really change. The loss doesn't really change, or it changes very little. That's how we know that we've kind of converged at a local minimum. And so every single one of these jumps is one pass through of the algorithm.
Yeah, and we're gonna discuss this algorithm in detail in the coming slides.
Mm-hmm. Right. And I think that's the only thing I wanted to talk about there. So another thing was the learning rate. So the learning rate is something that we can adjust with, we can adjust as a hyperparameter, right? It's something that we set at the beginning of our training process, and then that kind of determines how fast it makes those hops. So in this diagram, we can see that our choice of learning rate can actually affect how well it converges to a minimum, or whether it converges or not. So if we pick too small of a value, then what might happen is that every step is very, very small, and it's going to take a very long time to converge. Another problem is that if the steps are very small, it can get stuck at very small, like local minimums. Like if there was another hump and then another drop down here, then this algorithm would never get to that point, because every single step is very small, and once it reaches that minimum, it's just going to kind of stay there. Same problem, or a different kind of problem, might happen when we pick a learning rate that's too large. In this case, we start somewhere like here, right? And if our learning rate is too large, it's going to say, okay, well, we need to move to the left in order to reduce the loss. But what's going to happen is it's going to move too far to the left and overshoot the minimum, and go to a point where it's even further, where it has an even higher loss. And then it's going to go, okay, well, we've done even worse, so we need to move in the other direction even more. So then it makes another jump, but this time it increases the cost even further. And every time it makes a jump, the cost keeps increasing, and it never converges. It just diverges to infinity. So the learning rates you set is going to depend on the algorithm that you have. Like with gradient descent, a default might be like 0.1 or 0.01. And if you're using a framework with like PyTorch or TensorFlow, a lot of the times they actually set those defaults for you, and you can probably just use them. But you can take a look at how your algorithm is learning, like every single step. Okay, well, it's learning very slowly. Maybe we should increase the learning rate, or maybe you watch training and, oh, okay, it's the loss is increasing every step, so that's a problem. We need to decrease the learning rate. And that's how you can kind of tell which way you need to adjust the learning rate in order to optimize your training.
Yeah, so like Ben said, guys, so the learning rate is a hyperparameter, right? Which means we as the engineers, have to decide what a good value for this will be for our model in our particular case. It's not something the model can learn on its own. It's something that we have to figure out. And usually hyperparameters have to be determined empirically, right? There's no really like mathematical formula that you can throw your other variables into and then it'll spit out a learning rate for you. That really doesn't exist. There's various methods in terms of the way you train. There's things called cross-fold validation and whatnot that isn't important right now, but there's various methods you can use to basically empirically determine by running a bunch of experiments, okay, what's the best learning rate for my particular model? Because there's just so many different variables that go into determining what a good learning rate is, that the best way to figure it out is really just to play around with it a little bit. For the sake of what we're doing, you can kind of just stick with these default values like Ben stated, and they're going to work fine for basically everything we're doing in advanced workshop.
So now we're going back to neural networks. You might recognize some of these slides. In contrast to logistic regression, neural networks we're sort of stacking these logistic regression models together. Each of these nodes are artificial neurons. There we go. And each node is sort of like its own logistic regression model. So it has its own parameters. These weights are independent of every other node, its own bias, which is also independent of every other node, and an activation function. And this activation function is something like this slide here, which is sigmoid. And this activation function takes the output of the hypothesis function, that linear hypothesis function that we showed earlier, which can have a value between negative infinity and infinity, and maps that to a value between 0 and 1. And in a way, this sort of mimics how biological neurons kind of, they might have other neurons that are connected to it that might give it a signal. And if the signal reaches a certain threshold, then it goes closer to 1, and then it propagates that to the next nodes, the next neurons that are connected to it.
Yeah, I actually think the name activation function comes from the term in biology. I think it's called activation threshold, right? So like when you have a neuron in your brain, if you guys in high school, you probably learned in a biology class, right? That if a certain voltage or whatever, a certain strength voltage is sent to the next neuron, then it'll keep relaying the message on and on and on, right? And then that's how signals get transferred throughout your brain, right? But as soon as you don't hit that threshold, you're not going to be moving it forward, right? So that's not exactly what's happening here, but that's a good way of thinking about it. It's a good inspiration for seeing that when values tend towards 1, then it's going to keep propagating throughout our network. And when they're tending towards 0, they're going to keep diminishing and diminishing. And a lot of times it also makes sense when we're talking about binary classification tasks, right? If this is your output layer, if you're getting a value of, for instance, above 0.5, then that could mean to the model, then yes, I'm affirming like that this is like a cat, for instance. And then if it's like below 0.5, you could be like, the model saying, no, this is not a cat, right? So there's always that threshold to think about when we're looking at the activation function.
Yeah, another thing I want to note is that this is not the only possible activation function. There are other activation functions that you can use. Like with logistic regression, we only kind of looked at this function, right? We wanted to output a value between 0 and 1, but we don't necessarily have to restrict ourselves to that. There's another activation function called Rayleigh. We don't have a slide on that, and we'll talk about it later, actually, in a different workshop. But the key point with the activation function, it has to have some nonlinear. It has to be a nonlinear function. It can't be. It can't just be a line, right? You can't have an activation function that just multiplies our hypothesis function, the x times w plus b, by just a constant value. Because if we do that, then when we chain together a bunch of, or if we compose together a bunch of these logistic functions into a neural network, like in this slide, if we connect them together, then if you just distribute the, wish I made a diagram for this, but
I think this will be a lot more clear. We have slides that
yeah, we have slides on it later, but I just wanted to make the point that this is not the only activation function, and the activation function needs to have some nonlinearity to it.
Yeah, it's important basically that we're restricting the range of our outputs, right? Because when we look at the linear function, right? So if you can go back to the previous slide for a second, Ben.
Yeah.
So when we're looking at the y equals our sigmoid times the quantity of our hypothesis function, right? So this x w plus b is a linear function, right? So its range is unbounded. It can be anywhere from -infinity to infinity, right? So we're gonna see that in the future that's gonna cause a lot of problems in terms of the way our algorithms work when we're training our models. So it's just important to note, it's really important that we're restricting our range of outputs in some manner, and that's a big reason why we have that's one of the big reasons why we have activation functions, along with many other reasons. So yeah.
And this is just comparing logistic regression and neural networks. So you can see that logistic regression or neural networks are just like logistic regression, but you have more than one of them, and you can have more than one layer as well. So the output of one logistic regression node kind of feeds into the next one, feed forward network.
Yeah,
But,
and what I know we keep kind of heuristically and hand-wavingly telling you guys like, yeah, we're like stacking a bunch of these logistic regressions and not really giving you a good idea of what that really means besides this visual. It's gonna make a lot of sense throughout when we get to the next few slides. So don't worry if you're not exactly sure what we mean by like stacking a bunch of logistic regressions together. That's what the point of the next few slides are.
We're really hand-waving a lot of this stuff, but I feel like once we get to especially convolutional neural networks, it gets a lot more intuitive. And actually, this next slide, we're going to play a little bit of a video. But if you have some time, this is actually a really great video explaining neural networks, and it gives you that intuition of like why does having more layers or more neurons, or what does it actually do to make it to give it more predictive power. But I'm going to skip to 842, and it's going to talk a little bit about why we have biases and why biases kind of like considered a little separate to weights. They're kind of trained in the same way, but they have they play a bit of a different role. So we're going to go to 842. It's not going to talk about biases right away. It's actually going to give you a little bit of context first, but it's going to reach it in about 2 minutes after this.
Yeah, so let's just play the video. Make sure the audio is working. Can you? So we have to share audio, Ben. So can you reshare? Little checkbox on the bottom left. So yeah, just make sure you share audio.
I got it.
The hope is for one particular neuron conceivably combine pixels into edges, or edges into patterns, or patterns into digits. And to zoom in on one very specific example, let's say the hope is for one particular neuron in the second layer to pick up on whether or not the image has an edge in this region here. The question at hand is, what parameters should the network have? What dials and knobs should you be able to tweak so that it's expressive enough to potentially capture this pattern, or any other pixel pattern, or the pattern that several edges can make a loop, and other such things? Well, what we'll do is assign a weight to each one of the connections between our neuron and the neurons from the first layer. These weights are just numbers. Then take all of those activations from the first layer and compute their weighted sum according to these weights. I find it helpful to think of these weights as being organized into a little grid of their own, and I'm going to use green pixels to indicate positive weights and red pixels to indicate negative weights, where the brightness of that pixel is some loose depiction of the weight's value. Now, if we made the weights associated with almost all of the pixels 0, except for some positive weights in this region that we care about, then taking the weighted sum of all the pixel values really just amounts to adding up the values of the pixel just in the region that we care about. And if you really wanted to pick up on whether there's an edge here, what you might do is have some negative weights associated with the surrounding pixels. Then the sum is largest when those middle pixels are bright, but the surrounding pixels are darker. When you compute a weighted sum like this, you might come out with any number, but for this network, what we want is for activations to be some is called the sigmoid function, also known as a logistic curve. Basically, very negative inputs end up close to 0, very positive inputs end up close to 1, and it just steadily increases around the input 0. So the activation of the neuron here is basically a measure of how positive the relevant weighted sum is. But maybe it's not that you want the neuron to light up when the weighted sum is bigger than 0. Maybe you only want it to be active when the sum is bigger than, say, 10. That is, you want some bias for it to be inactive. What we'll do then is just add in some other number, like -10, to this weighted sum before plugging it through the sigmoid squishification function. That additional number is called the bias. So the weights tell you what pixel pattern this neuron in the second layer is picking up on, and the bias tells you how high the weighted sum needs to be before the neuron starts getting meaningfully active. And that is just one neuron. Every other neuron in this layer is going to be connected to all 784 pixel neurons from the first layer.
So there's a lot more to that video, and it's really great as well. So watch it if you have time. But I hope you guys understand a little bit better why we kind of like always talk about this bias a little separately. But at the same time, we do train it in the same way. We train it with like the same algorithm, and we treat it kind of the same way, same as a weight in that sense. But when it's making predictions, it does really play quite a bit of a different role.
Yeah, it kind of goes back to that analogy of the neuron again, right? Where of the biological neuron, where we really care if it's hitting a certain threshold, right? So if we really, so for that example with the edge that he was talking about in the video, if we care that that edge is very, very prominent, we want it to be very, very distinct and very, very clear that there's really an edge there, you would probably assign a bias that, like a very large bias in the negative direction, like 20 or something, right? And then that would mean that you have to have a very large value from your W1x, W2x, blah, 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 in order to actually see an activation there. So it kind of forces the network to make very decisive decisions and very confident decisions. So that's the way I like to think about the bias. So
Right.
do you have anything else to say there, Ben?
No, that's all. You got it. Thanks.
Okay, cool.
After this, I think, Paymon, you are going to take over talking about backpropagation and training.
Okay, so I'm gonna share my screen now, just so you guys can see my cursor when I go over things. Okay, cool. Let me just go to the slide we're on. Okay, is everything good, Ben and Justin, or everyone else? Yes.
Looks good to me.
Okay, awesome. So this is where I kind of recommend maybe you guys get a note sheet out if you don't already have one out or something. There's going to be some things that you want to write down. Like in particular, I would think this slide is pretty helpful to write down as we go through it. So this is kind of the like 7 pillars, I guess, of kind of how you would train a single input. And by single input, I mean a single training example. So for example, we're going to be looking at the case of training handwritten digits a lot as we go through this further, as we have already touched on a few times. So when we're training training a classifier to recognize handwritten digits, the inputs are going to be images, right? They're going to be images of some handwritten digit. So when we say a single training example, in that case, we're referring to a single image. So that image could be an image representing a hand-drawn number 8, for example. And then the network's job would be to classify that as the actual digit 8 in the computer, right? So the first step we need to do in general is we need to define the architecture that we want to be using for a task. So You guys see in parentheses, I say fully connected CNN, RNN. So these are different model architectures. Right now, I just want you guys to pay attention to the thing that says fully connected. The kind of network we're going to be looking at today and the kind of network you guys just saw in the video and that we discussed last week, we refer to as fully connected networks. And that's just because, as the name implies, every neuron in a single layer is connected to every neuron in the previous layer by a weight, right? Which is exactly what the guy in the video just said. Okay, so that's why it's called a fully connected network. And this is often the first kind of network people look at. It's the simplest and the most easily digestible. There's also different model architectures, which we're going to look at later in future workshops, called CNN, so convolutional neural networks, which we'll be looking at next week, RNNs, recurrent neural networks. The point is, all of these different model architectures are suited for different use cases, have different strengths and different weaknesses. And it's up to you as the engineer to decide for a given problem, should I be using a CNN, an RNN, a fully connected network? What should I be using in order to maximize my result or get the task done, right? Because at the end of the day, as an engineer, all you care about is when you want to get to some output, you want to get to some finished product, and you want to figure out the best way to get to that product. So you got to define the architecture. For the sake of this workshop, we're just saying fully connected. Now, determine the number of inputs, hidden layers, and outputs. Okay. So for inputs, it all depends on what data set you're using, right? So I'm going to keep going back to the handwritten digits because that's what we're going to be using. For our handwritten digit data set, each training sample, so each image is a 28 by 28 pixel image, okay? And if you do 28 times 28, well, that gives you 784, right? So each pixel will have a certain value associated with it from 0 to 255. 0 would be a black pixel. 255 would mean a completely lit up white pixel. Okay, so each pixel has a number between 0 and 255 associated with it, and there's 784 of those pixels. So that means our input layer is going to have 784 of those neurons, okay? Because we need to be able to account for all 784 of those pixels when we're training our model. Okay, the hidden layers. So the hidden layers are, I'm just going to go to the next slide just for visual purposes for a second. So the hidden layer, if this was our first layer, if this was our input layer, so we would have 784 of these. And then our hidden layers would be here in the middle, right? So you have to first decide how many hidden layers you want, and you have to decide how many neurons you want in each hidden layer. So for example, if we're pretending that this layer 1's an input layer, this layer 2's a hidden layer, and this layer 3 is an output layer, then we've decided then for this model that we're going to have 4 neurons in our hidden layer and that we're only going to have 1 hidden layer, right? But you could have also chosen to have 10 neurons in this layer. You could have chosen to have many hidden layers. You could have like way more hidden layers than just this 1 hidden layer, but you decided that you only want 1. And we discussed last week briefly the implications of having larger models, right? We said you're going to have more bandwidth kind of to play around with. You're going to have a much more capable model with much more potential, but you're going to need a lot more data to train it, and it's going to be more subject to overfitting and things like this. So it's always a trade-off, and you have to kind of judge on your own as an engineer. You have to look at the complexity of the task you're trying to solve and be like, okay, do I need a really strong network here? Do I need a really large network, or can I just get away with something smaller and save some space and time? Okay, so you have to determine all of those things. Then the outputs, right? So when we're classifying digits, there's 10 different digits, right? So that's we're doing a multi-class classification problem where the network could give us one of 10 different answers, right? 10 digits, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. It could tell us any of those. So our output layer is going to have 10 different neurons in it. Each neuron is going to correspond to a digit. And whichever neuron our neural network ultimately pings at or lights up the most, or assigns the highest value to, is going to be its prediction. Okay, so if the neuron for the digit 1 lights up with a value of like 0.85, for example. So remember, we squish it into a sigmoid, so the range is between 0 and 1 for each neuron, right? So if it gives us a pretty high value of like 0.85, chances are, if that's the highest value out of any of the 10 values that it's talking about, that the network's predicting that the input you gave is a 1. Okay, so that's step 2, initialize weights and biases, right? So we discussed this last week. to do this for our case, we're just going to be simply giving them random values. Let's just say random values between -1 and 1, right? So for the sake of, for now, we're just going to be initializing these randomly. There's some things you can do to make it more likely to be towards values that would be more optimal for the network, but we're just going to be doing them randomly for now. Okay. Now this is where we get to the kind of new stuff where we haven't talked about. So you see the two words in caps, feed forward and back propagate. We're going to be talking in detail about what both of these things are. So feeding forward means that basically you send the training example through your network, right? So you send the inputs into the first layer, you kind of calculate all of these hidden layer values, and then that ultimately gives you the output. That gives you the prediction. So it's basically passing your training example into your network and seeing what it outputs, right? That's what feeding forward is. And then once we have an output, once we have a prediction from the network, remember we have the label. We have what the value should be, right? Because we're doing supervised learning, as we discussed last week. So we can compare what the network outputs versus what the label is to determine the loss. And then after we determine the loss, we can determine the output error, which is a metric we're going to discuss in more detail, which is going to help us get started on how we should update the network. So we determine the output error using the loss function. Then once we have the output layer, we're going to use this very famous algorithm called back propagation in order to actually update the weights and biases in our network. This is ultimately how the network's actually learning. When people talk about machine learning and how neural networks learn things, it's using this algorithm. Backpropagation is how the weights and biases actually get updated. So we pass backwards through the networks, and you'll see why it's called backpropagation, because we kind of go backwards from the last layer and update things, blah, 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 all the way until the beginning. So we update everything. And then once we have those updates, we first calculate how we should update it, and then we update it. So those are kind of all the steps. So you do that every single iteration that you want to train. And we're going to discuss in more detail what that means. So I just talked for a really long time. So I want to, I'm sure a lot of you guys probably have some questions about this. So I'm going to pause for a second here, and please unmute with any questions you have about anything on this slide. We're going to be talking about feeding forward and back propagation in detail throughout the rest of the workshop. Let me also open the chat on my end so I can kind of see what's going on. Okay. Okay, well, if we don't have questions, I want to at least get some confirmation that we're making sense here. So can you guys say in the chat, like, if you're understanding what I'm saying right now? Is there something that's not clear?
Yeah, you can also do like a react, like thumbs up if it's clear, thumbs down if it's not.
Okay. Well, it sounds like you guys are getting what we're talking about for now, so that's good.
Can we also get a quick gauge on like the pacing of the workshop as well? Is it good for pacing for you guys?
Cool. Okay. And
Awesome.
also, we're probably in a few minutes, we're probably going to give you guys a 5-minute break. We didn't do that last time, I think. Darren, great question. We're going to be talking about that. So I'm going to have to delay your question just so we stay on track. But that's something that we're going to explicitly discuss. So good question. Okay. So I'm going to go through a few more slides, and then we're going to give you guys a 5-minute break, and then we'll continue. Okay. Cool. So I'm going to be discussing some notation now. So this is kind of why I said you guys should hopefully have a note-taking apparatus out so you can kind of write some of this stuff down, because understanding this notation is really important for understanding the backpropagation and feeding forward algorithms and what's happening. So yeah, so try to stay as focused as possible here, because you might get lost if you're not careful. Also,
but if you do have questions, like if the notation is confusing, because it is going to be like notation you haven't seen before, it's not like standard, please like tell us, let us know in chat or interrupt us, so that we don't move on without clarifying.
Yeah, I'm going to spend a lot of time on these next few slides to make sure you guys really understand this notation. Also, this book that's hyperlinked here is like fantastic. So 3 blue, 1 brown. That's the name of that YouTube channel. I'll write in the chat. 3 blue, 1 brown. That guy makes some awesome YouTube videos. He makes awesome videos about linear algebra, which is really important for machine learning. He also makes a bunch of those machine learning videos. He's great. Also, this book is extremely great if you guys want a really in-depth kind of understanding of backpropagation and very fundamental machine learning mathematics. This book is great. And a lot of what I'm about to talk about is adapted from this book. Okay. So without further ado, let's talk about the notation. So I discussed with you guys briefly last week that when we're looking at this kind of model of the neural network, each of these lines kind of represents a weight, right? And it represents kind of the weight that the output of this neuron, for example, has on this neuron in the next layer. And when I'm saying this and this, I'm referring to what I'm pointing at with the cursor, right? So like this line, whatever weight it has refers to the weight that this output has on what this output is. And then that is also influenced by this neuron because there's this connection here, this neuron, and then this neuron, right? So like I said, it's fully connected. So every neuron in the previous layer goes to every neuron in the next layer, which should be clear here, right? Just by looking at these lines. So each of these has a weight associated with it. So there's a specific notation we're going to use when we're referring to these weight values, okay? And it's going to make sense. It might take a second to sink in, but it'll make sense, okay? So this so Matthew, great question. It's not extremely standardized because in machine learning, there's kind of a lot of different ways that people like to think about things and kind of explain things. So like it's not like in math where it's like the plus symbol means addition everywhere, right? And everyone knows it's not quite like that. But what's really important here is that you guys need to at least understand some notation or standard in order to understand the algorithm. What's the most important is that you understand the algorithm and what's going on. And then from there, you're going to be much more adept at kind of reading papers and kind of making sense of information that's maybe presented in a slightly different way than the way you're seeing it here, as long as you understand the algorithm. Okay, so let's talk about the notation. So you guys see this arrow is pointing to this specific line. So it's referring to the weight value that is connecting this neuron in the second layer to this neuron in the third layer, right? So the superscript here, so the superscript is the number on the top. The superscript refers to what layer this kind of weight is pointing to. So it's pointing to layer 3, right? So we put a 3 up here. So that's all that superscript is. The 2 refers to the neuron number from top to bottom in the layer that it's pointing to. Okay, so this neuron at the top is labeled number 1. This neuron right under it is labeled number 2, right? So that's why there's a number 2 here, because it's the second neuron in the third layer. Okay, and then the second subscript, the 4, refers to, as you guys probably can guess by now, the neuron that's being referred to in the previous layer, right? So this 4 is referring to the 4th neuron in the second layer. Okay, so that might take a second to make sense. So I'm going to ask you guys a few quick questions. I just want people to quickly unmute and kind of give me an answer. Okay, so I'm pointing to a neuron right here, or sorry, not a neuron. I'm pointing to this arrow right here. Can someone tell me how you would represent that in terms of this notation? This one on my cursor. Just quickly, someone unmute and go for the answer. We don't want to spend too much time here.
W211.
Yeah, so W 211. Okay, so that's correct. So the 2, so when he says 2, he's referring to the superscript, right? So the superscript is 2 because it's pointing to the second layer. And then the subscripts are both 1 because it's the first neuron in both of these layers, right? Now, is anyone not clear on what that means? Just say yes if you're clear, say no if you're not clear in the chat. I appreciate you guys giving the feedback there because it helps us gauge if we're doing a good job. Okay, cool. Okay, so that's really important. Okay, now that was how we notate kind of the arrows, right? The arrows represent weights. Now there's some values that are inherent to the neurons themselves, right? So some of those values are the biases and the activation. So for the sake of the way we're going to explain this, each neuron has a bias associated with it and an activation associated with it, right? So the activation is kind of like how when you're passing the training example through the network, it's kind of the output of that neuron. Okay, so you can think of that value A, the activation, as the output that neuron's giving, right? So when I was talking about earlier in the output layer, if the neuron representing the 1 gives you a value of 0.85, that would mean that the activation is 0.85. Okay, so each of these neurons has those values associated with it. Now, it's probably pretty clear to you how this notation works, right? But I'll quickly go over it, right? So the superscript, like before, refers to the layer that we're looking at. So this is the third layer. So we have a superscript of 3. The subscript refers to the neuron within that layer. So it's the third layer, it's the first layer, it's the first neuron in the third layer. So we notate it as such. The notation is exactly the same when we're referring to the biases. You're in the second layer and you're looking at the third neuron. So we say B superscript 2 subscript 3. Okay. I think that's clear to everyone. If you guys understood the weight one, I think this is easier, right? So yeah, I think that's clear. If you guys aren't clear, just let me know. Okay. Now this is where you guys gotta just stick with me here and really ask questions if you're not sure about something and whatnot. Okay. So this should look somewhat familiar to you guys, right? This is just the much more mathematically explicit and precise kind of formula where we're talking about W. This is kind of, you guys can see like the WX plus B kind of thing, and then we apply the sigmoid. It's the same idea here. It's just a much more precise way of looking at it. And what this is basically saying is that we take, so, okay. Let me just explain things here first. Okay, so you guys should hopefully understand this notation. So this is telling you how to find the activation for one specific neuron, right? So it's telling you how to find the activation of some neuron in the Lth layers, the jth neuron in the Lth layer, to be precise, right? So, and what that means is that we're going to iterate over k neurons, and this k refers to the number of neurons in the previous layer, right? Because if we recall, this second subscript here refers to the neuron in the previous layer, right? So when you see this WJK, it makes sense, right? That you're iterating over the number of neurons in the previous layer, okay? So to give you some intuition for that, when we want to compute the activation for, let's look at this one that's labeled here with the bias. If we want to find the activation for the third neuron in the second layer, we need to kind of compute all of those little WX values, right? For each of these 3 lines, right? So we first do the WX for this one, this line that goes from this neuron to this neuron, then the one that comes from this neuron to this neuron, and then the one that comes from this neuron to this neuron, right? So we compute those 3, and then we add them together, right? This is a summation. And then after we add all of them together, we add this, whatever this bias value is that is inherent to this neuron. And this is exactly what you guys saw in the video earlier. There was a perfect kind of visual of that where you kind of add up all of the weights associated from the previous layers, and then you apply the bias. Okay. And then after you do all of that, this is some linear function as we've been discussing for the past 2 workshops, right? So from there, you need to apply the sigmoid to normalize it to a value between 0 and 1. Okay. Is there anything unclear about what I just said? This is the formula to compute the activation for any given neuron in the network. So please say yes if it's clear, or if it's not clear, please let me know it's not clear about this. Okay, awesome. Great. Okay, this is just kind of another visual to kind of show you guys what's going on, right? So yeah, so here we have 3 neurons going into, so 3 neurons in the previous layer, 3 neurons in this layer. So if we want to compute the activation of this neuron at the top in the second layer, right? So we take this arrow, and this arrow. You see those 3 arrows, you can trace them back, and they each go to one of these neurons. And then you compute this sum for across all of these 3 arrows, and then you apply that bias at the end. And then this little sigmoid here is saying you apply the sigmoid to whatever you got there. And then that gives you the activation. So if you guys, just in case it's not clear, right? So before we were kind of saying we were referring to A as X, right? In the formulas, we kind of, the heuristic formulas we showed you guys before, it was like an X, right? So the X is kind of the same thing as the A here. You can kind of think of it in the same way. Okay. We're just using the A just because that's what they use in the book, and it's and it stands for like activation, right? So Kyle asks, why is the first subscript 1 a 1 and not a 3?
That is
Sorry.
my bad.
Okay,
I
yeah,
missed that.
that's a typo.
Yeah, that's my typo. Sorry
So
about
this
that.
should be a 3. Good catch. We'll fix that after this workshop. Thank you. Okay, now, this is what I was talking about with you guys last week, where I said we were first gonna show you guys kind of how to do it for one neuron, and then we were gonna show you kind of the matrix linear algebra way of thinking about it. Because in reality, the computer is gonna be computing like all of the activations in one layer at once, right? And it leverages the tools of linear algebra to do that. Okay, so this is the formula to calculate the activation for every neuron in one layer. So if you guys read kind of what's written here, right? So it kind of outlines to you guys what each of these things actually represents. I'll also say it verbally, right? So AL is going to be a vector, right? And each entry in that vector represents the activation of one of the neurons, right? So if we're looking here at A21, A22, and A23, all three of these activations would be stored in a single vector that has 3 different elements in it, right? And then each of those values would just refer to one of them. The first value would refer to this neuron, the second one would be the second neuron, the third one would be the third neuron, okay? And we're gonna have a visual that will make that a lot more clear, right? So we're computing them all at once. So how do we do that, okay? So it's really important that we understand the dimensions of the things being multiplied here. Otherwise, we get confused really fast. So WL is a matrix that represents all of the weights connecting one layer to the next layer. Okay. So in this example, and in any of the kind of neural network pictures you guys have seen in the past, right? The WL represents all of these lines, right? So if we're computing the outputs for this layer, that WL refers to all of these lines. So this one, 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 every single line that you see between layer 1 and layer 2 is encoded in WL, okay? And it's organized in a specific way that we're going to explore in a second, okay? And then AL minus 1, or sorry, AL minus 1 refers to all the activations in the previous layer, right? So this should be understandable, right? It's kind of the same idea as this AL, where so in this example, if our AL is 3 entries because this layer has 3 entries, well, if we're looking at AL minus 1, that's also going to be a vector that has 3 entries, right? Because we have 3 neurons in the previous layer as well. Okay, and then BL. So I'm gonna pose this as a question now. Okay, what for this example on this previous slide here with the 3 neurons, how many elements would the matrix or the vector BL have in it? And someone feel free to unmute or say in the chat what you guys think. Okay.
3 by 1.
Yeah. So 3 by 1, right? So 3 rows, 1 column. That's correct. And it makes sense, right? Because first of all, we're gonna explore this more deeply, but first of all, we need to make sure we're doing valid operations, right? You can't add a 3 by 1 vector with like a 5 by 1 vector or something, right? That doesn't work. You can't do that. So we need to first of all make sure we have valid operations. So it intuitively makes sense that this one would have 3 entries, right? But also another way of thinking about it is that, right, we said earlier that each neuron has a bias associated with it, right? So then it becomes obvious from that point that if each neuron has to have a bias associated with it, and there's 3 neurons in this layer, then, well, there has to be 3 biases that are being encoded, right? So this is kind of that formula to compute everything at once. So intuitively, I'm sure you guys can kind of see how that's related to this one, right? It looks pretty similar. Just we kind of removed the subscripts and it kind of looks nicer, right? But in a way, it's kind of more confusing because we don't really know how this actually multiplies things correctly, and how we're actually getting the correct answer from this, and how we're not like maybe multiplying an incorrect row by an incorrect column. So now we're going to make it clear in a second, like why this actually works. Okay. But just bear with me. This is one more notation thing we have to go through. So ZL is a value. So when we put the 3 lines here, this just means we're defining ZL ourselves in this specific way. We're defining ZL as basically the value you get from the linear output, right? Because AL technically is the value you get after you normalize it. Okay. So when we say AL here, right, that's after we pass it through the sigmoid, right? So we're just going to define this value ZL, which is the value you get before passing it through the sigmoid function. Now you might be asking like, oh, why is this necessary? Like, what's the point? You'll see it makes a lot of the math for the back propagation part a lot easier to understand. It's just a way of kind of visualizing things and making things a lot easier to understand. So just know that when we say ZL, we're talking about the I think it's called it's referred to as the weighted input vector, right? So it's just what we get before we pass the sigmoid. Okay. So that's what that means. Now, this is just that same visual we showed you guys before, showing how this kind of weighted input is playing into it. So yeah, it's just the value before you pass it to the sigmoid. Simple enough. Okay. Now, this is a very important slide because it is going to kind of make it clear why this actually works, right? So I'm sure you guys hopefully like are familiar with the way in which matrix multiplication works. We're kind of going to go over that a little bit here if you're kind of rusty or whatever. But if you're familiar with the way matrix multiplication works, it will become very elegantly clear in a second how we can just use this kind of formula right here to just kind of do all of this for all the neurons at once, right? So if we go back to this, okay, first I'm going to ask you guys a question. So obviously this calculation is going to be giving us the weighted input for a certain layer in our neural network. So the 2 questions are asked here. How many neurons are in layer L? So layer L is the layer that we're trying to calculate the weighted input for. And then how many neurons are in L-1, which is, what we're using to calculate the weighted input in L. So can someone maybe unmute and give me your answers to these questions and maybe a justification using what you're looking at in these equations?
I believe the neurons in layer L are going to be 3.
Okay.
Or-
How did you get 3?
Oh, hold on. I'm thinking of the number of outputs. Yeah, okay. And then L-1 is going to be 5. I figure
Cool.
that's the case because we are taking a 5x1 vector, which is, I believe, to be our input vector. And then
right
we are
here.
multiplying it by our, I forget what you called it, the weight vector matrix, something like that.
Yeah, just the weight. Let's just call it the weight matrix for now.
Okay, weight matrix, which represents the weights of that connect one neuron to every neuron in the output layer.
Yeah. So precisely what's happening here is, so this first row that you're looking at in the matrix, right? It's looking at, so there's 5 neurons in the previous layer, as we just established, right? So all 5 of those neurons in the previous layer need to influence the activation of the first neuron in our output layer, right? Like just like so, like here, right? So this one has to influence it, this one has to influence it, and this one. Every neuron in the previous layer has to influence every neuron in the next layer, right? So if there's 5 neurons in the previous layer, that means there needs to be 5 weights that connect each neuron in the layer we're trying to calculate to all of the neurons in the previous layer, right? Because here there was 3 neurons in the previous layer, right? So there's 3 of these arrows. Now, if there's 5 neurons in the previous layer, there has to be 5 of those arrows, right? Each of those arrows represents a certain weight, right? So it makes sense that there's 5 values here, right? So this represents the first arrow that points to the first neuron. The second arrow that points to the first neuron, the third arrow that points to the first neuron, so on and so forth. And then this represents the first arrow that points to the second neuron, the second arrow that points to the second neuron, blah, 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 so on and so forth, right? So let's look quickly what happens when we actually perform the matrix multiplication, right? So when you perform matrix multiplication, what are we doing? First, well, okay, I want someone to kind of unmute and kind of explain like how the matrix multiplication kind of like in what order things are multiplied and kind of how this makes sense. There's nothing special here. It's just we're multiplying two matrices, just like you learned in math class or whatever, right?
For the first matrix that you're multiplying, the number of columns has to be equal to the number of rows in the second part of what you're multiplying by.
Yeah, that's correct. Now, okay, yeah, that's correct. So can you maybe explain, like, I kind of want you guys to see how doing that matrix multiplication is the same thing as doing this formula, this component formula, except we're doing it for every neuron, except we're doing it at once, right? So do you guys, I want you guys to kind of see how this is the same thing.
So like when you do the matrix multiplication, you would
Yeah.
multiply the one by the A1, and then 1, 2 by A2. And so essentially you multiply each of these like to their respective terms, and then you add it together to get the Z value.
Yeah,
Pretty much.
that's correct. Okay, so basically this formula is doing this kind of, because we have 3 neurons in the output layer, right? Or the layer we're trying to compute. This is the same as, so we would normally have to do this component one 3 times, right? Because we have 3 neurons in the output layer. So we'd have to do this for these 3 arrows that go to this first neuron. Then we would do it for the second neuron. We would do it for this arrow, and this arrow. And then we get another value. And then for the third neuron, we would do it for this arrow, and this arrow, right? So you do it 3 times and we get 3 different outputs, right? Because ultimately this formula only gives us 1 output for 1 neuron. Now, what you're doing when you're doing this matrix multiplication is you're doing exactly what you're doing before. It's just you're doing it all at once. And the reason we just do it like this, and the reason it's important to understand what we're doing here, is because this is what the computer does, right? Because it's a lot, because matrix multiplication and matrix operations are heavily optimized in computers, especially in GPUs, right? Which is why you see GPUs being used for training a lot. These operations are extremely optimized. So it's a lot faster for you to just do all of these at once using matrices than if you had to go back and do this for every single neuron. It would not be computationally feasible. Okay. So this is important to understand. Okay. And I think most of you guys kind of see what's going on here. Okay. So let me make sure everyone understands what's going on here. Can I get some yeses, some nos about what's going on here? Awesome. Okay. So what's the big picture here, right? So what we're doing here is basically pieces of the feeding forward process, right? So when I was talking about feeding forward earlier, right? Feeding forward was how we get from our input to our output, right? And to get from our input to our output in a neural network, we have to kind of pass through this gauntlet of a bunch of these hidden layers, right? So because you have to compute each of these things at a time. You have to compute this output, and then you have to use this output to get to the next one, until you get to the output, right? In a kind of iterative process, right? So that's exactly how we feed forward, is using this exact formula that we just explained. That's exactly what we do. So we just do this over and over again until we get to the output, right? So for example, in our input, yeah. So let's pretend this is the whole model, right? Usually your model will be bigger than this, but let's pretend this is the whole model. This is your input layer. This is your you have one hidden layer. This is your output, right? So when we feed forward, we need to basically apply that equation, this matrix one. We need to apply it twice, right? The first time we apply it, we get the activations for our layer 2. And then the second time we apply it, we get the activations for our output. Now, someone tell me why it's only 2 times and not 3 times in the context of like when you're actually solving a problem. Like for this specific model, like why don't I need to use the formula to figure out what goes in layer 1? Can someone answer that for me?
That's your input layer.
Yeah, right. So it's the input. It's the input layer. So we already have the values. They're going to be some number between 0 in for the case of our MNIST. MNIST is that digit classification class. It's going to be that number between 0 and 255. So right. So we just throw that number into this first layer, and then that's how we get the first layer. And then we do this for this kind of formula twice. Once to get the activations for our hidden layer, and then another time to get the activations for our output layer. And then we're done, right? We're done feeding forward. We have the output. The last line, line of neurons is the output, right? So we have the output at that point. Okay. Just a quick thing to note before we get into the next part. We're gonna do like a 3-minute break. We need to actually go a bit faster, so I'm gonna not 5 minutes, but just a quick note: when we say capital L in the future slides, it refers to the output layer. Okay, so yeah, that's how feeding forward works. You use this formula for each kind of layer in your network until you get to the output. Okay, so let's reconvene at 7:28 exactly, and then we will dive into backpropagation because we only have 30 minutes left, and this is kind of beefy. So I need to make sure we have time for that. So yeah, let's see you guys in 3 minutes.
If you guys have any questions in the meantime, you can also ask. I'll be here.
I have a question.
Yep.
So basically like the activations are like the inputs each time after the first one, right? Like the first one we have actual inputs.
Mhm.
And then the activations are kind of taking the place of those inputs.
That's right.
So the initial inputs are like in the one example with like the letters or the numbers, like identifying them. It was a number from 0 to 255.
Yes, let me actually get to the slide so we can talk about it. Sorry, I was going ahead a little bit. So what were you talking about again? Can you repeat it?
So like the initial inputs we have for like from going from 1 to 2. And then
Okay.
every time after that, instead of like X values, like inputs, it would be A instead, like the previous A vector.
Right.
But then like in the example he was talking about, we had like 0 to 255 for the inputs.
Yeah. So what happens, right?
example?
So I can answer this.
Yeah.
So wait, are you sharing, Ben? Okay.
Yeah, I'm sharing. I'm trying to find that slide.
Here, I can just do the sharing.
Yeah.
Okay, so 0 to 255, right? So let's go here, right? So if the inputs are 0 to 255, so you pass that value, right? That value that's between 0 to 255, you pass it through this formula. And what ultimately happens is you're going to be given an output and an activation here that's between 0 and 1, right? Because you pass that AL minus 1, right? So you're in this case, right? Your inputs for between 0 and 255 are going to be one of these values, this AL minus 1. And then you multiply it by whatever this weight vector is. So that's represented by these lines once again, right? And then you add your bias. And then you throw all of that through the sigmoid, right? And that sigmoid is going to compress it down to a 0 and a 1. So your inputs aren't necessarily going to be between 0 and 1. Your inputs can be in a different range. It's just that everything after the input has to be between 0 and 1, okay?
So my question was like, why do we need all the activations to be 0 to 1? But then why don't we like run the sigmoid on the initial input? Like why is it?
So you could do that if you wanted to. It's just not necessary.
Yeah, so you could do that, and 0 to 1 is not mandatory. It's only a result of the fact that we're using sigmoid here. Like if you use a different activation function like ReLU, which ReLU we haven't talked about yet, we'll talk about in a future workshop, but it's basically everything below 0, every number less than 0 maps to 0, and anything beyond that maps to just itself. So it's the identity function greater than 0 and 0 when it's less than 0.
Yeah, long story, we gotta get going because I don't wanna.
Yeah, I think I got it. I think that makes
But
sense. Thank you.
basically, long story short, activations are really important for keeping our values like regularized and in check. If you're not doing anything to keep your values kind of in check, they're gonna kind of explode, and then it's gonna be bad. They're gonna get like really big or really small normally, and we're gonna explore that in future workshops. But it's that's an important reason why we have activation functions. Okay, back propagation. Okay, so we need to understand feeding forward to understand back propagation, because to do back propagation, you need to have an output. Okay, we're starting at the output now, right? Think of everything backwards from feed forward. Okay, think of everything backwards now. So now we have an output. Now we're going to figure out what we need to do from that output in order to update the weights and biases in our network. Okay, and I'm going to try to make as many analogies as possible to the feeding forward algorithm, because I think that one's a lot more understandable in a lot of senses, and it's a lot clearer what's going on. For a lot of it, it's more simple. So I'm going to try to convey what's happening in terms of feeding forward. Okay, so back propagation is the algorithm that we use to update the weights and biases in the network. Now, this is the same book that I kind of was talking about earlier, and that hyperlink up there. I'm not going to go back, but this is that same book, and it's just it links you to the specific chapter about back propagation. And here's a list of proof, like a really like sketchy like note paper like a list of proofs I did on the equations we're about to go over. I'm not gonna like go over them because it would take forever, but I did the proofs for all of these equations that I'm about to show you guys. So if you really want to understand it more, like please look at that. And then if you have questions about it, ask me in the Discord later. Okay, what is backprop, right? So we have the cost, right? So this is just pretend this is like the same cost function we were talking about earlier, right? Like nothing's changed, right? This is like the ALX, like that's the activation of the output layer, right? So it's A is the activation, the L superscript means the last layer, right? So these are the activations of the output layer, and then the Y refers to like the actual label, right? In our supervised learning model. So this is the kind of the same formula you guys saw before. You compute the difference, you square it, you do whatever, right? So our ultimate goal in backpropagation is to find these two nice values, for every instance in the entire network, because we have a bunch of weights, right? We have all of those arrows, so many arrows, right? We have a bunch of weights, and we have a bunch of biases. One bias basically for every like neuron in the hidden layer and the output layer, right? So we have a lot of weights and a lot of biases. And for each of them, we want to compute the partial derivative of our cost function with respect to these values, okay? Because ultimately what our cost function is a function of these weights and biases, okay? So if we find an approximation to the gradient of this cost function, that kind of tells us what direction we need to move the weights and biases in order to kind of converge to that local minimum that we've been talking about this whole time, right? So because the cost function and the network itself is a function of these weights and biases, the goal of backprop is to approximate that gradient, not give you an exact value, but approximate it. Use that approximation to then update the weights and biases in the network to give you a lower cost value. And that's how we're converging on that local minimum. Okay, so that's the intuition behind what's happening. Now we're gonna talk in a lot of detail how we basically calculate all of these. Okay. Oh, there's some stuff here. Yeah, this is what I just said. So, oh, and then quick note, error. I'm gonna be referring to another value, which is very important in backpropagation, that I'm referring to as the error. Okay, error and cost are two different things. Cost is that value you get when you throw your prediction into this cost function, right? And then you get this C value. That's your cost. The error value is something different. And we're going to basically calculate an error for each neuron. We're going to calculate an error. And then once we calculate those errors, we can use those errors to update all the weights and biases in the network. Okay. And you'll see what I'm saying in a second. So this is the error. So the error is the derivative of the cost function with respect to this weighted input. So remember, this weighted input z is just the value you get before you apply the sigmoid, right? It's the value of the activation, but like before you apply the sigmoid. And you may ask like, well, why is it z and why is it like not a? And well, you'll realize that there's no reason to have to deal with the sigmoid here. It just makes everything a lot messier than it needs to be, and you basically achieve the same result. So that's kind of why I defined that z for you guys earlier. So this error, so you see that we say error, the superscript L, the subscript J, same rules as we talked about before. So what this implies is that each neuron has an error associated with it, right? Okay, so our goal is to calculate the errors for each of these, okay? So I'm gonna open the chat again just in case people are asking questions. Cool. Okay. So we just define this as such, okay? And our goal, and you're gonna see in a second that defining this quantity and calculating this specific quantity makes it really easy to find this quantity and this quantity, okay? So if we can compute the partial derivative with respect to this weighted input, it's really easy to compute the partial derivative with respect to the weights and with respect to the bias. And intuitively, this makes sense because what is z? Z is like wx plus b, right? So z is a function of w and b, right? So if we have some sort of encoding of the partial derivative with respect to z, it should make sense that we should be able to derive the partial derivatives with respect to w and b, because z is just a function of w and b. You need w and b to get z in the first place, okay? Any questions about that?
Real quick question.
Yeah.
So do we find cost and error like for every neuron and every layer?
So cost and error are different, right? So cost is that one value. So you calculate cost at the end of one feeding forward session, right? So let's say for MNIST, I pass like an image through my network and then I get an output, right? I get a single output and that's that vector that's like 10 entries, right? Because there's 10 different digits. I use that vector output to calculate. So that would be this vector, okay? This ALX. And then I use that with the labels that I'm already given in the data set to calculate the loss. So the cost / loss or whatever is calculated once. So you calculate the loss at the beginning of backpropagation, okay? So that's like, it's kind of the last thing you do in feed forward, right? You get the cost, and it's like the first thing in backpropagation. So now we have this cost, and then we use that to calculate the error. But you're correct that we calculate the error for each neuron. So yes, that's correct. But I just want it to be very clear that the cost and error are different. Is anyone not sure what the difference between the cost and the error are? If you are sure, say yes. Okay, I am not seeing a lot of yeses. So no. Okay. So someone says no. So the cost, right? The cost is like we calculate. So you have some training input, right? So that's one image of like a 5. Like it's that 28 by 28 image that's composed of a total of 784 pixels, and it encodes a handwritten 5, right? So yeah, so I know it does go 0 to 100, but we're trying to go through it as slow as possible, so it makes sense. But so you have that image, right? So we do the feeding forward part. We do that thing that we just talked about in the previous half of the workshop, where we throw it through that matrix operation, like however many times we need to, right? So we do that for every layer to get from one layer to the next layer. That's how we calculate all those activations, right? We calculate each activation one layer at a time until we get to the output layers of activation, okay? So we get to the output layers of activations. That's what this vector is, okay? Now, once we have this vector, we compute a single value. Okay, it's one value. And that value is called the cost. Okay. And that value is gotten by kind of taking the difference between the label, so what the output should be and what the output is, right? And then we do this squaring operation, and then we add all of them up, and then we average them, and that's mean squared error. Okay, so that's what the loss is. Okay, it's one value. So at the end of that sample, you get one value. That's what loss is. Now, error is a quantity that is inherent to every neuron. Okay. So just like, so I'm sure what you guys understand, right? How we discussed this earlier, how every neuron has a bias and an activation when we're doing feeding forward, right? Every single neuron has that activation, it has that bias. Just like every neuron has that activation and that bias, every neuron has this third quantity now that I'm defining as the error. It's just another quantity that's inherent to the neuron. And the goal of back propagation is to calculate those errors in each of those neurons. Okay. So the cost is just that value you get at the end of your feeding forward. And it tells you kind of how well you're doing. Okay. And then we use this error to update the weights and biases so then that our cost will go down even more. Now, is anyone still unclear? If you are, it's like literally completely okay. Like I promise, it's okay.
Another
So
way,
just to clarify, like for let's say a network with 5 layers in total,
Sure.
then how many costs do we find? Is it just 1 or is it 4?
1. You get the cost at the end of after you feed forward through the entire network, you get your output. The only thing you use to calculate the loss or the cost is that output. Okay, so you only get, each time you throw through a training sample, you get one value for the loss. Okay.
I could try to word it in a different way. So the cost is how the overall network is performing,
Yeah.
and the error is how much does each neuron contribute to that cost.
Yeah, that's a great way of thinking about it.
All right, thank you.
Okay, so I feel like most of the confusion is caused by the fact that their names are similar. Just pretend that their names are not similar. Okay, this is a value inherent to one neuron, just like the activation and the bias. Okay, and then the cost is a value inherent to the entire network. It's saying, look, you did this well at predicting this input. So when I pass the 5 and it gives me a number for the cost, it's like the lower that value is, the better job I did of predicting that that's a 5. Okay. So let's move on from that. So our goal at this point is to calculate all of these errors. Just like, so I was trying to tell you guys how we were trying to make analogies to feeding forward. So the job in feeding forward was to calculate all of the activations layer by layer, right? Okay, now the job of back propagation is to compute all of these errors layer by layer, except instead of going from the beginning to the end, now we're going from the end to the beginning, okay? So our job is to compute all of these errors layer by layer, and you're going to see that in a second, okay? Now, this is just a quick thing that you guys need to understand about the formulas I'm about to show you. So this is like when you use this kind of like symbol with the dot in the middle, that's referring to element-wise multiplication, right? So this is not like normally how matrix multiplication works, right? Like I'm sure you guys understand that. This is not normally how you do matrix multiplication. The difference here is that I'm just doing it element-wise, right? So I'm taking this element and multiplying it with the same corresponding element in the next matrix. And then that's my output for the same corresponding value in the output, so on and so forth. So for element-wise, right, you have to have the same dimension in each of the things that you're multiplying, right? Is anyone like unclear what this means? Like it's like how you do addition, right? It's how you do addition in matrices, except instead of addition, you're just multiplying them now. Can I get a yes if that's clear, or no if that's not clear? Okay, cool. Yeah. So just keep in mind, like that's what it means. Okay. It's just important notation so we can show you the formulas. Okay. A lot of math on this slide. So let's go slow. Okay. So I'm gonna keep making analogies to to feeding forward. Okay, so remember with feeding forward, remember how we didn't have to do anything to get the input activations, because the input activations are just the input values, right? It's just we already have those values, so we don't need to do any special formula for that. Okay, we already have it. It's already given to us. Okay, but in our analogy here, remember we're computing all the errors from the last layer to the first layer. Okay, so the analogy is that in backpropagation, the errors are like the activations in the feeding forward. Okay, and then instead of going forward from the first layer to the last layer, we're going from the last layer to first layer. Okay, now we already had the input activations, right, in feeding forward, but we don't already have the output errors. Okay, we don't already have the output errors for that last layer in our neural network. Okay, because like I said earlier, right, every single neuron needs to have an error associated with it, including every neuron in the output layer. So it's not like feeding forward where we have the input already, right? We don't have anything. We need to actually calculate those errors in the output layer. And then once we calculate those errors in the output layer, we can do something very similar to what we did for feeding forward, except we do it backwards. Because once we have the first one, it's the same idea. You just use the first one to get to the next one, to the next one, and the next one, and the next one until you're at the beginning. Okay. So we need to use this special formula in order to tell us the errors in the output layer. Okay. So this formula in component form is the derivative of the cost with respect to the activations of each of the neurons in the output layer multiplied by this weighted input passed through the derivative of the sigmoid function. Okay. Now, you're probably saying like, whoa, like, where did this come from? Like, how did you get this, right? So if you're really, really curious of where this came from, it's in the proof, okay? And it comes from how we defined this error, because like it all comes from how we define this error, right? Because we're calculating errors, so it's kind of all based on the way we defined errors, and that's all explained in that Paymon proof tiny URL. Okay, so this is the formula in component form, and this is that same formula in vector form. Okay, so this kind of upside down triangle represents gradient. Okay, so this is saying the gradient of the cost function with respect to the activation, which is a vector, and then we do the element-wise product with this derivative of the sigmoid function for the weighted output. Now, in this instance, right, the for mean squared error, right, this is a more generalized form of the equation, right? But for mean squared error, the activation, the derivative of the cost function with respect to the activation is this value. Okay. So this value here, the partial derivative, the derivative cost with respect to the activation is equal to this quantity. Okay. For this specific cost function. Okay. So, but if you're using a different cost function, it's going to be different. Okay. But for this one, it's this cost function. Okay. Now, this will hopefully make things make more sense. So, in vector form, right? So, in this instance, someone tell me how many neurons I have in the output layer. The answer is what you think it is. So, just someone shout it out.
5.
Yeah, 5, right? So, for every neuron in the output layer, I first calculate the derivative of the cost with respect to the activation. So to do that, it's this value, okay? So we compute this value. Then we multiply it by the weighted input of that exact same neuron, but we pass that value through the derivative of the sigmoid, okay? So you recall that we don't have to recalculate ZL because we already have ZL because we just did feed forward, right? So if you recall, it's impossible for us to do back propagation if we don't feed forward because we need these values. We need all of the values that we got in the feeding forward to do the back propagation as well. So this ZL, we just got it when we did feeding forward. So we already have this value. So we just have to compute this and we have to compute these values. Okay. And then we find the element-wise product between each of these things. So this guy multiplied by this guy multiplied by this guy, so on and so forth. And then that's going to give us another 5 by 1 vector, right? Which is equal to the error of the output layer, right? So we're going to get 5 values, and each value represents the error in each corresponding neuron in the output layer. Okay. So now we have the error in the output layer. Okay. So if there's 5 neurons in the output layer, we have the error for all 5 of those neurons now. Okay. So I anticipate that there will be a few questions about this. So I'm going to take a second for you to guys to maybe ask some questions. No questions? Do you guys get this? Or is there anything confusing about it? Basically, what you need to understand is this value is dependent on what the cost function is. And this value we already have computed from the feeding forward. And then you just pass it through whatever your activation function is. Okay. Can I get a yes or a no in the chat, please? I feel like this might be a bit confusing. Okay. It seems like most of you guys are getting it. Okay. So this is analogous to kind of how in feeding forward, we have our inputs. We kind of just calculated our inputs, except now we calculated like the inputs for back prop, right? So we kind of found our first layer now. Now that we have this first layer, we can, we can use it to find the errors in all the layers before that, up until the first layer, okay? So this is the equation that we used to do that. So once again, there's proofs of all of these equations in that paper that I linked to you guys earlier in the slide. And then also that book, all of these equations are explained thoroughly in that book, okay? But this equation now that we're looking at right now is analogous to the equation that we used earlier for feeding forward, okay? Think of it like this equation, okay? So we use this equation. Given the activation of the previous layer, we can find the activation of the next layer, and then we can keep doing that, right? Now, this equation that I just showed you is exactly the same thing, except now we're doing it backwards. So from the end to the beginning, and instead of calculating activations, now we're calculating those error values, okay? So it's actually extremely similar to the formula, right? You can see the analogy, like how it's analogous, like almost perfectly, right? You have like the W times like the value that's inherent to the neuron. And then before, like we had some plus B, but instead now we're multiplying it by this value. Okay, so it's actually very similar in a lot of ways. It's very analogous. So once again, we already have these ZLs. We have all of these Z values, and we have all these weight values already, right? So all we're doing is using the error values to get the error values in the previous layer again and again and again. So to visualize that, what we've just done is here. So the thing we did in the previous equation is we calculated all the errors for these neurons in the output layer, right? So the first equation I showed you guys calculated these two errors. Now, Samuel says, what does transpose means? I'll get to that in a second. So we calculated the errors in this output layer. Now that we have the errors in this output layer, we can use the formula that I just showed you guys on the current slide that we were looking at to calculate the errors in this. And then we can do that again for this one and so on and so forth. Okay. So it's like the feeding forward, but backwards. I know I keep saying that, but it's like, I think it's a really helpful way of understanding it. Okay. Now, Samuel says, what does transpose mean? So transpose means you swap all of the value. I wouldn't worry about it. It's just so that the matrix multiplication is compatible. The transpose means you swap all of the rows and columns in the matrix. So if you have if you have a row of values here, that's now the first column instead of the first row, and then you do that for all of them. That's what transposing means. That's just what it means to transpose a matrix in general. Okay. Yeah, you can. Yeah. Because if we don't do the transpose, I'm not going to get into the details now because we don't have that much time. But if you don't do the transpose, basically, if you have like an A times B times a C times D matrix, you need. So I'll write in the chat, in the Zoom chat. So if you have an A times B times a C times D matrix, you need B and C to be the same. Otherwise, you can't do otherwise it's not compatible. That's a rule of how matrix multiplication works. So if you don't do the transpose, the multiplication is not compatible. Okay. So that's why we use the transpose. But basically the intuition behind this and what's actually happening is you do this. So you have the errors in the output layer. Now you throw the errors of the output layer into this equation, and then you get the errors in the layer before that. You do that again, you do that again, and then until you get all the errors. Okay. So let's visualize that again. So we kind of have a big guy here. So what this matrix is kind of saying is that, okay, let's ask that same question again. So how many layers are in the L plus, so how many neurons are in the L plus 1 layer, and how many neurons are in the L layer? Can someone answer for me? So a good hint is like, this is the error. These are the errors of the L plus 1 layer, right? These are the errors of the L plus 1 layer, and there's 5 of them, right? And we know each neuron needs to have an error, right? So someone said 5 and 5. Okay, that's not quite right. It's almost right.
And 5.
Yeah, it's 7 and 5. Do you want to explain why?
If you like multiply the big matrix with like the ones on the right, it's the big matrix is a 7 by 5 multiplying by 5 by 1. So then the result of that would be a 7 by 1.
Yep, that's a great way of thinking about it. So based on what I just talked about with the ABCD thing, so this is a 7 by 5 matrix multiplied by a 5 by 1 matrix. So the output is going to be an A times D matrix. And here our A is 7 and our D is 1. So you get a 7 by 1 output. So that means we calculated the errors of all 7 neurons in the previous layer. Okay. So now you do this, you go back, that gives you the errors for 1 layer back. You do it again, 1 layer back, blah, blah, blah. Okay. Same idea. Now, that's basically backpropagation. That gets you all of those errors just by doing those 2 equations, right? That's like great, right? So like if you were worried that like it gets even crazier, it doesn't get much crazier than that. You just use those 2 equations and it'll get you all the errors. Now the last step is, how do you get because remember, ultimately what we wanted to do was compute the derivative of the cost function with respect to each of the biases and with respect to each of the weights, right? So we have all the errors. Now, how do we do that? These formulas are how you do that, right? And once again, there's proofs for why these things are true in the Paymon proof thing. But basically, the error is actually literally equivalent to the derivative of the cost function with respect to the bias for each neuron. So it's literally equivalent, and you can see why that's true if you look at that paper. And then we can use this formula just to get the value for the weights, okay? So now basically we have formulas that will give us the derivative of the cost function with respect to every bias in the network and with respect to every weight in the network, okay? So this is just a quick summary of all 4 of those integral equations that we just talked about. So a brief recap, and if you guys didn't write them down before, I think you guys should just like write it down somewhere. So brief recap, this is the equation you use to determine the error of the output layer, so the final layer in the neural network. So this is kind of what jump starts your back propagation, what gets you started. It gives you your first values that you need. And once you have that, you can kind of use this and then use the second equation to jump off of that, right? Because now you have the errors in the output layer. You have a starting point. Now that you have a starting point, you can go backwards, 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 backwards until you're at the beginning. And then once you're at the beginning, now that you have the errors for all of the neurons, you can use that to calculate these bias and weight partials using these 2 equations. And that's just the direct calculation. You just run the error through this, and you'll get that value. Okay. So I'll stay on this for like 30 seconds, and then I'll give you guys a quick big picture. It's almost 8 o'clock. So we actually didn't get through the whole workshop, which is a bit unlucky. We got almost through all of it. Thankfully, the next workshop is not as long, so we should be able to wrap up the this workshop and then get into the CNN stuff next time. But yeah, so hopefully you guys got that down. And I think it's probably appropriate to just stop here. This is basically the formula that you're going to use once you calculated all those weights and bias partials in order to actually do the updates, right? Like we calculated the partials. Now we need to use those partials to do the actual updates in the network. So this is what you used to do that. We're going to stop here. So I'm not going to really break this down. We'll start off here. But just something to note, right? So you update the weights and partial, like you do everything we just said. Let's say you do everything that we just said throughout this whole workshop. You feed forward, you use all those equations, you feed forward, you get your output, you get your cost, you use the formula to find the output error, you use the next formula to find all the other errors, then you use the other formulas to find all the weight and bias partials. You do all of that stuff, right? And then you update the weights and biases. Now, your question is, am I done? Is my network trained? The answer is like no, which might sound scary, right? Because you're like, wait, I just did all that work. But the answer is just that you have to do this process many, many times, right? And this whole process that we just described kind of talks about one iteration on this little thing. You see these little iterations here. That whole process is kind of like one little step downwards, right? And then each time we do that whole process, we take another step down, another step down, another step down. So we do this whole process that we've discussed today many, many times over a certain number of iterations, and we'll discuss this more in the SGD algorithm next week until you converge at this minimum. But that process is basically how you take one step towards this minimum. So that process is like this little x to this x here. It's taking one step. And then you do it over and over again until you converge towards your minimum. So yeah, we ended up here at, where is it? Slide 39. So we're almost done. Just a few more slides about how we basically actually perform that update, which we'll talk about with you guys next week. This is good though. I think you guys have a lot to think about because I think we've gone over a lot of pretty heavy stuff this week. So we'll all four of us, me, Vaishnavi, Ben, and Justin, will be looking through the Discord and answering your guys' questions. Yeah. So like Vaishnavi said, that's like a lot of content, and I understand that. I understand that some of it might not be entirely clear to you guys. So I think a great thing you guys could do is in the Discord, if you're not sure about a certain slide, just like talk about the slide you're unsure about or the specific question you have, and we'll make sure to like answer for you guys as soon as possible. And then last closing remarks. Sorry for going on, but last closing remarks. I highly recommend that you guys look at this this reference, this neural networks and deep learning book. It is what these kind of slides were adapted off of, so it'll give you a lot more deeper understanding of stuff. There is a link to the slides. It is right here. This tiny URL right here. Justin, if you want to paste I think Ryan already got it for us. Thank you, Ryan. Yeah. So make sure you get this link. I think it's important you guys have this. And yeah, that kind of wraps it up. Justin or Ben or Vaishnav, do you guys have anything to say?
No.
Yeah, just.
Or you go ahead.
Again, that was a lot of content, so just take your time to digest it. We're gonna stay for a couple of minutes just to field any questions that you guys have. So feel free to just shout them out if you don't have any questions. Thanks for coming. Ben, do you have anything to add?
No, it's just the same thing. Like talk. I know like you guys probably won't have questions right away. It's gonna take some time, so feel free to use the Discord.
And also, before you guys go, can we get you guys to fill out the feedback form? We didn't get to the end of our workshop, but we'd still appreciate a lot of feedback on the content that we did cover.
Right. Let me actually go to that slide so you guys can see it.
Yeah.
Yeah, it's if you guys have a link to the slides, it's literally the last slide.
Yeah. You guys should see it now. It's 8-track feedback. It's the same feedback format for all the workshops. You just select a different workshop for it.
Yeah, it's the same form. Like you guys can like literally, if you guys want to be like homies, you guys can like bookmark that for us, and just like it'll be there for you.
Yeah, it's nice.
Also, one last note: don't feel like you need to understand everything from this workshop to come to the next workshop. Because I know that's something I did when I was attending workshops. A lot of the workshops will kind of be like individual too going forward. But as long as you have a vague understanding, just like show up to the workshops. and try to get as much as you can.
Also, great news. This is, I think, definitely the hardest workshop to understand, like by far. So, if you guys like, yeah, like I really wouldn't worry about it if it's like not 100% for this one. It actually, I think it gets easier to understand. It gets more intuitive. It gets more high level. We just delved into the really low level aspects of kind of how we're actually performing updates, because it's just a very fundamental skill that I think, and we all think that all machine learning engineers should understand before they just like hop into like PyTorch or whatever. So don't worry about it, and we're here to answer your guys' questions.
Yeah, it's not the math is just, it's good background to have, but it's not going to be necessary technically for the next workshops or even the project in that matter, because we're going to be using high level libraries. So you're not going to be like actually doing these calculations and doing it
Yeah,
from
like
scratch
I
with
remember
NumPy.
last time Justin and I were teaching this last time, and like I remember the third workshop, what we did is we did like
NumPy.
actual low level implementation, yeah, using NumPy, without using like any high level machine learning libraries, and like that was kind of, I feel like that was kind of rough for people, but this is, it was also, I feel like in a sense it was also good because people get more exposure to this kind of what's going on here, but like, yeah.
Yeah, it's a bit off topic, but yeah, it was that NumPy thing was actually adapted from a class that goes over, yeah, Stanford's class.
Stanford, what is it, 239?
Yeah, so it's definitely, I think, not conducive to like this once a week workshop format. That's why we removed it and replaced it with a more friendly to project.
But something to take away from that is that there's so many really in-depth resources. Stanford CS 239, all there's YouTube videos of all of their lectures. They give great explanations of backprop, like really detailed, by the professors at Stanford. And that book, I cannot emphasize how good that book is, that we referenced at the beginning of the backpropagation portion. It's like really great. And 3 Blue 1 Brown is like really great as well. His YouTube videos are also really great. So
I guess if you get anything from this workshop, you got lots of resources to learn more.
The book is online. Like, yeah, like just literally press that link in the slides. If you look up neural networks and deep learning on Google, it'll like come up. Like it's a free book by Michael Nielsen online. So
awesome. So like we said, we're gonna stick around for a couple minutes and just field some questions if you guys have any.
Yep.
In chat or out loud. We'll be here until you guys leave, basically.
Yeah. Or until you realize you're away from keyboard, that too. Don't count you? Okay, we won't count.
Thanks, see you Monday.
Okay, everyone's gone except for Kwa. So
all right.
Kwa,